Welcome to the lecture 9 of machine learning course. In this session, we are going to talk about two important concepts called the curse of dimensionality and PCA. So, and we would also see an application of PCA that is very prominent called Eigenfaces in this particular session. So let us start our discussion. So in this uh, in this slide, you can see some of the data over here. Okay. So if I ask you that what is the dimensionality of this data, can you tell me what is the dimensionality of the data? Can anybody type? 2, because it's a two-dimensional data, x and y, two-dimensional data. Every item has a 2 attribute. So dimensionality of the data is 2. However, if you see the data into this particular direction, okay, then do you think that still the dimensionality is 2? Answer is no. That you can think that the data looks like the one dimensional, and whatever variation, because you see that the data are not on the same line, they will be going up and down. So they may happen because of some measurement issues. So you can think that it looks like the data is into the one dimension. If I see the data into from this particular dimension, so this is the important idea, that you change your perspective, then the data becomes better represented. So what happens that initially when you have a problem and you want to collect the data, you don't have any idea that how the data is. So you put various things to capture the, for example, some motion is happening over here, and you want to understand that how this particular motion is happening. For example, let me just quickly say that let's assume that there is a spring, and there is some item over here, and you have actually you have stretched it and leaved. So what happens that it is doing a SHM. We know that SHM happens, but let's assume that you don't know anything. You are the first one that who are doing the experiment. So you would be putting various cameras, one camera here, one camera here, try to capture that what is happening over here. So various cameras you would be deploying to see that what is happening over here. All these camera would give the different perspective, but what is the right perspective? What is the right way to find out? Because the readings coming from these cameras would be different. So you may be thinking that, okay, looks like that they all are different, but actually they are not really different. Actually, you must see into the motion into this particular dimension, and actually you are not capturing that. So this is very important that sometimes the data that you get may not be of the right, may not be the rightly represented, because this is going to happen because it's a scientific domain. So ultimately you initially you don't know anything. So that's why these kind of problem are going to happen. The data may be observed across different sensors. So the small variation would be due to noise. There could be small variation due to noise, and you think that that may contribute to the dimensionality. Okay. Sometimes it happens that, for example, in our example also, that you have seen that the motion is going to happen in this particular direction, but we are measuring that what is the variation in this particular direction, in direction. So what happens that it is going, looks like that it is moving from here to here, because if I'm measuring into this particular direction, so I would be seeing that the motion is from this particular place to this particular place. So and if I put another, for example, another camera here, another camera here, so I would be seeing that what is the motion is going to happen from here to here. So what would happen that if you are seeing the things from the different perspective and original thing you are not measuring, so you will also think that the various values, for example, the value that has been captured by this camera and value that has been captured by this camera may be related. Okay, they are related. However, their values are different. So it is possible that all the observations may not depend on the some quantity which is not being measured. They depend upon some quantity that is not being measured, but and that's why they are related. So it may also be possible the data is related. Okay. Uh, Here I want to clarify that what do I mean by the dimension. So dimension by dimension, I think you are very well you understand by yourself also that dimension means here the two-dimension data, as we have just talked about. So dimension actually talks about that what is the property you are measuring. Consider the example that we have seen, that whether the mango is ripe or not. In that example, what properties we have taken, what is the weight, what is the radius, into the, say, horizontal direction, radius in vertical direction, and what is the color, and similarly you can talk many things. For example, what is the softness? So anything somebody tells you that you are going to collect that data. Okay, so you may be thinking that if you collect more data, you are going to represent the item into the better way. So that's why people collect more data. And when they collect more data, the data becomes high dimensionality. The dimensionality actually increases. By the dimensionality, we mean that what is the attribute? What is the attribute? How many properties we are going to use to describe the item? Databases are generally into the high dimension because we don't know so we what is going to happen, so we want to measure as many things as possible. Okay, and one such example where the data is mostly very high dimension is the images. Okay, they contain lot of pixels, and the text, for example, the text, if you have a text file that you know that 2 to the power 6 words can be possible, but however you know that if the people uh, you may think that the person can write any words out of that, but however you know that not more than 2 to the power 4 number of words people use into the daily life. People use very small vocabulary. However, the possible words are very large. And into the images case also, for example, if it is a very small image, 250 cross 250, 250 cross 250. What do you mean by 2 cross 250 cross 250? It is a pixel. What is a pixel? When you see the image is actually a kind of small pixels. Okay, these are the values. They can hold some value. So there are pixel into the horizontal direction, pixel into the vertical direction. So this is the area in which all the pixels are there. Any particular pixel can hold any value from 0 to 255. So if you put any value, for example 10, if you put another value, for example 200, 205, then this particular pixel would be showing a brightness with as 10 brightness and 205 brightness. You can think that if the 255 is the full brightness, then 10 is going to represent some brightness and 205 represent a very higher brightness. So using this kind of brightness and darkness, so this creates a contrast, and then we can see that what is there inside the image. So what I wanted to tell, that if an image is given to you, for example, the image is given for the purpose of classification, and the classification could be, can you tell me whether in this image there is a aeroplane or car? Let's assume that this is what the question is, that in the given image whether there is a aeroplane or there is a car. So this complete image, in this sense, complete image is representing 0 and 1, whether there is a aeroplane or not. If airplane is not there, then there is a car, we are assuming. So we this complete image is with respect to the classification problem, is the data that you have in this particular image is only 1 bit. But how many bits are given to you? 250 cross 250. So many bits are given to you. So this is a problem actually, and the problem you can see over here. For example, in this particular image, the what is written on the screen? It is written 6. Okay, so if you want to write 6 into an image, so these pixels, the corresponding pixel, you have to make the black, and other pixels are actually white. Okay, but the data that it has is only 6. Let's assume the digits are from 0 to 9. So only 10 values you have. But how many values in this particular image representation you have? You have 2 to the, let's assume that this is a very small image, 20 cross 20. 20 cross 20 means 2 to the power 400. 2 to the power 400 different values are possible. If we assume that a bit can only have hold, let's assume that the black and white only. So two values are possible. So at this particular location, let's assume that only let's assume that the two values are possible. So how many such points we have? 400 points. Every pixel can have either switch on or switch off. 2 to the power 400 possibilities are there, and these many observations are possible, but meaningful things which are going to have, they are very less, because here you can see that the 6 is written, so it is a meaningful image. This image is also possible, this image is also possible, this image is also possible. So whether this image contains any of the digits, answer is no. this image contains no digit. However, the possibility of observation is this. So what I wanted to tell, if you complete, let's assume that this is a complete space of the possibilities, then the data is going to reside in very small space. Okay, all the things are actually some not possible. All the data values are not possible. So is it clear? All the values are not possible. Even this, if I change the bit, if I randomly change the bit position here and there, then you can see that the image actually get lost, and 6 is not no more there. So true dimensionality of the data, you can see that if you are able to represent all this space, if you are having the provision to store all these space, then it is useless because you know that the data is only coming from this particular space. Okay, because if these many bits are not there, then you cannot represent some of the things over here. But they are garbage. So true dimensionality, if you consider all those factors, that what are the available thing from where my data is coming, if you consider that particular thing, then you would be able to expose that what is the true dimensionality of the data. So in this particular example, let's assume that you want to represent the handwritten digits. Then what should be the right way to represent them? Is it if you don't want to use the images of that particular thing? So right thing could be that you use the something like the possible pen strokes. For example, what are the possible pen strokes? Okay, so what are the pen strokes here? Can you find out that what are the pen strokes here? So the first pen stroke is from here to here, then 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 here to here. 1, 2, 3, 4, 5, 6, 6 pen strokes. So to write a number, how many pen strokes you need? 10 pen strokes. So the true dimensionality of the data is actually, you can find out in this way. The true dimensionality of the data is actually very less, but we represent the data into the very high dimensional space. So why it is a problem? Okay, what the problem? Like let's be the data into the high dimensional space. Why it is a problem? So you understand that the one thing that till now we have understood, that the data that we have is most of the time have the high dimension. Is it clear to everybody? Okay. Now we are going to talk about that why it is a problem. Okay. Why it is a problem. So one problem is this, that into the machine learning ML based systems, into the ML based settings, what we do that if for a particular thing, if you want to if we if you want to find out that what is the probability, because you know that ultimately everything boils down to the probability, and then based on the probability we go for the classification that what is the what particular item it is. So you actually count the evidences, that what is how many time it has been happened. You actually go and count the evidences. So counting becomes difficult if the number of examples are very large. For example, if you assume that this is what the complete space, all the possibilities that you have, and this possibility, by this I mean that all the possibilities means even if the garbage possibilities are there, they are there. We have talked about that the actual data that belongs, it actually resides somewhere here. Okay, but you have the complete possibility. So and you are going to collect the data. Let's assume that your data collection method is going to give you the data from everywhere. Let's assume that the method that gives you the data is going to give you the data from everywhere. So what would happen? That because this is the complete space, so you would be assuming that data is if you assume that data is linearly data is independently and uniformly distributed, so data can come from everywhere. So whatever data you are going to have, it actually only small portion of that is going to represent the useful and right thing. This is the one problem, that if you assume that this is the complete space I have, if you assume that this is the complete space I have, and you generate the data uniformly, what would happen? That the data you are actually going to come up is actually absurd. There is one problem. Most of the data points that are going to they have the problem. They have the possibility of being absurd. So Let me give you a quick handle on that. So see this. Okay. See this, how many data points I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's assume that 10 data points are there into one-dimensional space. So you can see that there is a lot of crowding over here. So you can find out that the data items are nearby and you can do the processing. But if I divide them into two-dimensional space, so let's say this is the two-dimensional space, then these 10 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you can see that these 10 points are now separated. When I put the data into the two-dimensional space, you can see that they are separated. So here I could put the line, here I have to put a plane, but you can see that the data is actually sparse. The data becomes sparse. So looks like that, very important thing I'm going to tell, that looks like that here whatever data I had, lot of data I have collected and therefore I can do the processing. Makes sense? Here it looks like that these 10 items are lot of data items. I have sufficient number of data items I have collected, so I can do the processing, I can do the machine learning. But here it is sparse. So looks like that, okay, you should collect more data. Looks like that you should collect more data. And then only you would be having the representative data over there, then you can do the processing. So here we have a problem. Make sense? If we convert the data into the three-dimensional space, okay, then even sparse things are going to happen. So space is too much and you have only 10 points. So how come if you do the processing with these many small number of points, so whether your answer is going to be correct? So it looks like that. No. Okay. So you need sufficient data. So whatever data you have is actually not sufficient. It becomes insufficient if the dimensionality of the data is very large. So is it clear that your data becomes insufficient because the you whatever you can do as a human, you would be scaling up with a constant factor only. So you would be into the problem that to do the processing. Now let us talk about a very small thing. Let's assume there is a very important property that we are going to talk about. Okay, so this that we have just talked about that the density of the data decreases sharply with the dimension. So we have just talked about this, that the density of the data decreases when the dimensionality increases, and this leads to no observation for most of the cases. So there are no observation for many of the places where we have. Okay. So any question on this? Now I wanted to tell you a very important problem that also happens over here, that when your dimensionality increases, okay, so what happens that actually let's assume that this is the one dimensional data. So where would be the data point? You can say that data point would be here and here. Okay. But if the dimensionality increases, so let's assume that the hypercube, let's assume a hypersphere. So means it is a very dimensional, very high dimensional space. So into the hyperdimensional space, what happens that let's assume it's a d-dimensional data. All the data you may be thinking that where is the data? If I say that randomly you pick data item, let's assume that we are having the data item randomly. So where would the data item? Data item would be here. Okay, here itself. But actually this is not going to happen. What would happen that the data item would be here, all the data item would be into this place, into the very high dimensional space. Try to understand what I'm telling. Into the very high dimensional space, all the data belongs to the extremes. We would come to this particular point. Let us see a small mathematical derivation for that. All of you are ready? Should we go ahead? Say yes, that you are able to understand this. Can you write yes? You are comfortable? Okay. What I wanted to tell you that we have talked earlier that if you have a data item, so you can scale it into the unit vector into both the directions in all the dimensions. So it is not going to affect any way uh, your uh, your classification or whatever ML properties, they are not going to be violated. So you can do the scaling. So let's assume that the data is scaled and this is what the data I have. Let's assume that this is what the data I have. Okay, this is what the data item we have. Assume What is the length? We are assuming that the length is 1. Okay. We are assuming the length is 1. Let's assume that a small portion from here, this particular portion is epsilon portion, and here also I take the small portion of this. So I say that I draw a line over here. I say that when the data is here, then I say that data is interior, okay, is inside, and if the data is here, I say that data is on the border. Make sense? So in this particular cube, if the data point is here, okay, in here, then I say that it is outside or outer ring. It is at the border. It is at the border. And if the data is here, I say that data is into the interior. Make sense? Is it clear to everybody? Let's assume that I take the small distance from both the side epsilon and epsilon. I say that when the data is here, then it is inside. When here it is here, I say that it is on border. Clear? Yes or no? Say yes. Yes? Okay. So in this particular setting, let's assume that I have created the data. What I'm telling that this both the side very small. Epsilon is very small. Okay, epsilon is very small. So most of the data, what you expect? Most of the data, when you randomly pick the data would be here. Okay. Yes, you expect like that. So what is the probability that data would be here? It is 1 minus 2 epsilon. Probability that the data would be here is 1 minus 2 epsilon. Is it clear? Epsilon is a small number. Yes or no? Okay. Also, because two dimension I have, what is the probability that data would be inside into this dimension and also would be inside into this particular dimension? Epsilon inside into this particular dimension. What is the probability? To the power 2. What is the probability that it would also be into the 3 dimension? Because the third dimension is also there. The item would be here. A lot of space is there. Na? The probability is going to be this to the power 3. If it is n-dimensional data, where then it is going to be to the power n, the probability that the item randomly picked data item is going to be interior. This is the probability that the randomly picked data item is into the interior. Any problem? No problem. Let's assume the epsilon to be very small number is equal to 0.05. Okay. Then summation becomes 0.1, 0.9 to the power n. Okay. For example, if the n is equal to 100, let's assume that the 100 dimension data you have. If the n is equal to 100, means dimensionality is 100, then this number becomes 0.00026. Means what? 1000000. Out of 10 lakh data item, only 26 data item would be inside. So 0.9 to the power 100, this value comes out to be this. So what does it mean? That the probability of the data that it is inside is 0.00026. Means out of 10 lakhs data item, only 26 data item would be inside. So hope you understand this fact. Any question on that? What do I mean by this? I mean by this that if you consider a big space, okay, let's assume that the things are under the very hyperspace you just consider. So where would be the data point? Data point would be just few minutes back I told you that they are not interior. The probability of data point being on the interior is very less. So where the point would be? Point would be at the extreme. Okay, this is a big problem. That when you have a high dimensional space, then the data is mostly going to be on the space, only onto the borders. So what is the issue? Issue is this, that if you want to find out that which kind of item a particular thing, for example, I want to find out what kind of item this point is. So I have to see the other points which are into the nearby, and I can tell that, okay, it looks like that this item is of this particular kind. But because in this hyperdimensional space, you can see that this item is here and all other items are very, very far apart. So the concept of nearness, concept of nearness vanishes. No item is near. Everybody is on on the on the circumference. So no item is near. So machine learning actually fails in these kind of scenarios because you know that when there is no similarity between the item, finding out the similarity actually very difficult. Then you cannot go ahead with this. So this is the point that actually I wanted to make. In the high dimensional space, most of the data points lie on the edge, and that's why it is very difficult to go ahead with this kind of scenario. So you understand that what is the problem. So one solution could be that sometimes people can find out that, for example, this is a two-dimensional data. You can see that this is a two-dimensional data. This is two-dimensional data because the points are here, 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 here into this particular space. So it is a two-dimensional data. But somehow, I don't know how, like somehow if you can find out that they looks like that there is some curve that is going from here to here and the points are on this curve only. If you know that there is, and this is for example, you can say that there is a manifold or sheet, into this into the your dimension and the points are over there, then you can further simplify. You can tell that this item is at this particular distance, then you can measure the distance into this particular direction, and then you can reduce the dimensionality. How to find out this manifold for the given problem is I'm not talking about, but I'm telling that it is possible that you somehow try to somehow, if you know that where the what is the equation of the manifold, then you can reduce the dimensionality. Okay. Sometime if you want to understand that whether my data is two-dimensional data or three-dimensional data, there are some small hacks that you can apply, such as if you, for example, if you see the data points, if you have a data point and if you see that how many other data points are there into the two sigma neighborhood. Okay. For example, if you have a data point, you see that into the sigma neighborhood how many other data points are there. Okay. So you can see that means you know that various dimensionality are there with plus sigma and minus sigma. You see that you consider that particular area and see that how many data points are there, and then you increase from sigma to 2 sigma, and then you consider 2 sigma thing. Try to see that how many data items are here. If the data items doubles, means what? Looks like that your data is linear. If it becomes 4 times, looks like the data is into the 2 dimension. Become 9 times, 8 times, looks like the data is into 3D. Okay, so it looks like that the data is into 3D. Any question on that? Similarly, if you can find out that what is the actual dimensionality of the data. Now I want to bring you to the another part of this particular lecture. That is we want to talk about the PCA, and you know that into the data you know what is the mean, variance, and covariance. Okay, so if your data is there, so you can find out the variance of the data. That you know that the mean is nothing more than the summation of all the values and then divided by the number of items, and variance is actually means was this, then mean was this, variance is equal to summation of all the values, mu minus all the values, and you take the square and divide it by m. So mean and variance you can find. Sir, could you please repeat the previous point? What was the previous point? What was the previous point? Or what? Sanidhya? Tell me something. So you is this point? This? Yes or no? Sanidhya? Yes. So this is a simple point. Actually, try to understand that if you have a very high dimensional data, okay, if you have a very high dimensional data and you want to understand that what is the true dimensionality of the data, and d is equal to, for example, 100, but you want to understand that what is the true dimensionality of the data, and then and you assume that the data is a lot of data items, sufficient number of data item examples you have, and they are taken from they are randomly sampled from the space. Then you see that if you pick any data point and see that say epsilon neighborhood, you see that all the data point into the epsilon neighborhood. What do I mean by this? In every dimension, you add epsilon and subtract epsilon. So if there is any other point lying in that particular hypercube, you take that count that how many items are there, and then you see that how many data items are there. First you find out that how many data items are there into the epsilon neighborhood. Then you see that how many data points are there into two epsilon neighborhood. And if by increasing this number of points, earlier you find out the number of point where n, and now you find two n data points are there, means what? Items are doubling. Item are doubling. What does it mean? That my data is two-dimensional data or single dimensional data, because when I double the range, because into the two-dimensional space, if here till here if 10 points are there, so till here how many points would be there? 20 points will be there. But if it is a 2D space, so if you increase this, then this would also increase. So here you were actually earlier considering this space, now you are going to consider this space. If it becomes 4n, it means that your data is 2D data. Okay, and if it has been a cube, then earlier you are considering this space, now you are considering this space, it becomes 8n. Okay, so you say that it is a three-dimensional data. Make sense? Sanidhya, clear? Similarly, you can find out what is the number. So in this way, you can find out what is the true dimensionality, and then you can, since you know the true dimensionality, then you can reduce the data. So very important thing that you should understand over here is this, that whenever a data is given to you want to have the data in such a way so that everything is going to contribute to the data. All the data examples should contribute. If the same thing I'm going to have multiple number of times, they're not going to have any effect. So what is important that here, let's assume that A is this particular data and B is this, let's say n dimensional data I have. A and B are two data. So there is a concept that when you multiply these two items, when you multiply these two vectors, what you get? For example, if I want to find out A1 B1, A1 B1 plus A2 B2 plus A3 B3 and dot dot dot. If I want to find out the summation, what is this value? So you have to understand that if you know that from your vector understanding, that if there is a vector v and there vector u, then and there is a theta, then you say that cos theta is equal to v dot u. Okay, v dot u, vector v dot u, and divided by mod of v dot mod of u. Okay, this is what the equation is. So if also let us assume that the data are actually these vectors are unit vectors. So because in the direction, if we are only interested into the theta, we can assume that these vectors are unit vector. Then this vanishes. So this dot product actually is correspond to the cos theta. And when these two vectors are actually into the same direction, then what is the theta? Theta is equal to 0. And when the theta is equal to 0, this value becomes cos 0 becomes 1. And when the theta is 90 degree, one vector is here, another vector is here, then theta is equal to 90 degree, and then cos 90 becomes 0. So then it becomes 0. So two vectors, when they are into the same direction, when they are similar, when they are pointing to the similar direction, then the value is going to be, when they are pointing to the similar direction, then the value is going to be 1. Okay, otherwise the value is going to be 0. So if you take two vectors, okay, a and b, and you want to find out the multiplication, what you want, that they should be different, this value should be 0. When you are multiplying with own self, means then definitely you want to be very high value over there. You want here to be because the same vector is there, you want to be very high value over there. Make sense? Okay. So let us assume that you have x represent the data that you have, and x transpose. So x is the data. Let's assume that this is the data item that you have, and you put the x transpose. So again, this is the x transpose over there, and you find out the multiplication. You want to find out the multiplication, then this item would be multiplied over here, and you would be getting a value over here. then this value will be multiplied over here, you would be getting this value. This value will be multiplied over here, you would be getting this value. Similarly, this value would be multiplied by here, you would be getting this value. This value would be multiplied by here, you would be getting this value. Okay, this multiplication, and here if you apply the same concept, you would be seeing that this is the multiplication of the same item, this is the multiplication of the same item, this is the multiplication of the same item, different item. So these values should be what we want, these values should be 1. And what these values should be? These values should be 0. If it is like that, then only our data is actually rightly being seen. Then the data is my right data. So we want the data into this way that that this property holds, that all the diagonal elements are actually have a very high value, preferably 1, and the non-diagonal element have very low values, preferably 0. Okay. So okay. So try to understand that XX transpose, that the matrix that we have just talked about is a symmetric matrix. Is a symmetric matrix, because everybody okay? That this value and this value are going to be the same. It is going to be the symmetric matrix. And for a symmetric matrix, for this symmetric matrix, we can find out the eigenvalue decomposition. We can find out the eigenvalue decomposition. What is eigenvalue decomposition? So eigenvalue decomposition says that find out the eigenvector of this particular matrix. So this is a matrix, and if the eigenvectors are S, then S and lambda S transpose. So this is called the eigenvalue decomposition of a matrix. Okay. So I would not go into the much mathematical detail over here. What I wanted to tell you that are very simplified thing. I just found this particular equation. I just want to be comfortable, make you comfortable that a given matrix, you can do the for this particular matrix, you can do the eigenvalue decomposition, and if you do the eigenvalue decomposition, it has a property that there is a matrix S. The first matrix, it contains eigenvectors. So what is this? Eigenvectors, and this is the transpose of that thing, and in between there is lambda. Okay, there is lambda, that is a diagonal matrix, of eigenvalues. So eigenvectors and eigenvalues are there. So how to find out this, I'm not going to that detail, but I just wanted to tell you that consider this particular quantity. What is the S transpose into X? Consider this quantity S transpose into X. So everybody okay that this matrix, I can find out, if you find out the eigenvalue decomposition, then you can find out the value of S. This part is clear? If you find out the eigenvalue decomposition, then you would be able to find out that the matrix X having the eigenvector. This part is clear? Only this part. That if X is given to you, you can find out X transpose. From this you can find out S. This part is clear? Can you write yes? Nobody is writing yes. Naman? Yes? Yeah. So this part is clear that you can find out this as. Now I wanted to tell you, so in between I'm not talking about that how to find out this, that is we are not required at this particular moment. What I wanted to tell you that if you find out this S and then you multiply S transpose with the X, you use this and multiply this with the X, what would happen? Let's assume that by this you get another matrix Y. Let us find out what is the value of Y transpose. Y is a new matrix. So initially you had the matrix X, you have created a matrix Y. Okay. So Y is a new matrix. What is the value of Y transpose? Y transpose is equal to, because Y is equal to S transpose S, and then it is a transpose. Transpose says that X transpose and S transpose S, and their location changes. S transpose X. This value X transpose you know that S transpose because of this property, and then here S transpose S becomes identity, S transpose S becomes identity, so you get what? 1 upon n of lambda. Okay, so covariance matrix, this Y transpose is a covariance matrix. Covariance matrix of this Y is actually a diagonal matrix. because we know that this values, the matrix with the eigenvalues is such that only the diagonal components are there and all other values are actually zero. So we have actually, by applying this, by what I wanted to tell, by multiplying S transpose with the X, we got another matrix that had the property that that its covariance matrix is lambda. Make sense? Okay. So covariance matrix of this thing is diagonal. And what is the importance of this? That all the data are actually independent. So they are going to sit into the very different space, so that they are not similar. So all the data items that you have, they are unique and they are different. You have transformed the space in such a way so that all the data become different. Make sense? So is it clear that if you want to transform the data, there is a one method that you using eigenvectors, you can find out this as transpose X. So whatever new matrix, new data that you are going to get, have this property that all the data items are actually different. So, if this part is clear to you, I wanted to tell you that in the last class we have seen that any of the matrix can be can be converted using SVD into three part U sigma V transpose. We have in the last class we have seen that. Now, so here, what is the important? What was the problem, that this eigenvalue decomposition you cannot find for the all the matrices. If only if the matrix have some proper square format, then only you can do it. But here, you know that SVD you can find out for AD matrix. Okay, SVD you can find out. If you find out the SVD, you would be getting three things: U, sigma, V transpose. Last class we have seen that how to find out these values. I just wanted to tell you, consider this particular quantity U transpose X. Consider U transpose X. So what essentially I mean, that you have a matrix X, you have converted to using SVD U sigma V transpose. Now consider another matrix Y, that is U transpose X. And let me find out that what is the covariance matrix of this Y. So again, Y transpose, you know what is the Y value of Y? It is U transpose X, U transpose X, U transpose X transpose. So here again, this value becomes X transpose U, and then U transpose X. So here you see that that because of X transpose, X transpose is there, and U transpose is there. X transpose, you know that X transpose, you know that what is X? X is equal to U sigma V transpose. X transpose is U sigma V transpose. So it becomes V sigma U transpose sigma U. So this is coming from here. So what would happen? V transpose becomes identity. It becomes sigma square U transpose. Okay, so this quantity is what? U sigma square U transpose. You can see this here. So let me open it, and we can say that this thing again becomes identity, and this again becomes identity. So it becomes, so you get 1 upon n minus 1 of sigma square. Okay. So using singular value decomposition, SVD, we have seen that there is an eigenvalue, there is a relation between the eigenvalues. So eigenvalues and singular values are related. So lambda square, you have seen that they are going to be related in this way. That you have also seen that this particular matrix is also, this particular Y matrix is also such that its covariance matrix is a diagonal. Understand? So now again, the similar thing that you are going to have here, similar thing that you are going to achieve over here, you have achieved using the SVD here. Okay, and this is called the PCA, principal component analysis. This is called the PCA. What is it? That you take the X, you find out that what is the SVD component. You use the U and you multiply with the X, and whatever new matrix is there, it is a transform matrix of the X, and this represents the data better. So this is what the PCA is. What is the importance of this particular data? That all the data items are actually now independent. They are independent. So they are separated as much they are possible. Effect of PCA is this, that initially let's assume that these were the data points given to you, and if you see that what is their variance, so you can see that the variance is this much. So PC actually does that, it transform the data in such a way so that, for example, and now you can see that the data is actually rotated. So if you consider that you are shifted to these axes, okay, instead of that axis you are shifted to this axis. So now you can consider that this is the variance, because first data item is here and last data items is here. So you can see that the variance into this particular direction, the first vector direction, is larger as compared to the previous one. So your data is better represented when you apply the PCA on that. Okay, so there are less chances of the misclassification. There are less chances of misclassification. Here is an example. Try to be with me. So what I have did, I have used a LibreOffice means MS Word kind of thing to create a data where the first column is 1, 2, 3, 4, 5, 6, and all these three columns are actually random numbers. So I created using random number, I multiplied by 100 and taken the, so that because this is not a fractional number, taken the floor of that, I have created this data. Okay, stored in a file mydata.csv. Then I have this is the Python program that import pandas from PD scikit-learn. I imported the PCA. Then I have read this file, and then for all the 1 to 5, because 1, 2, 3 range 5 means 1 to 4, 1, 2, 3, 4. 1 to 4 items I am going to do. What I am going to do, I am applying the PCA, and number of component is I. What is I? I is 1, and then 2, then 3, then 4. So first I have applied only one. I have taken only the first component, and then I have applied PCA fit, and then try to find out that how much variance is of the data is being captured into the whatever I have used. And this is what the result is. Result says that when I have only one component, the variance is 38%. Okay, means this data, this was the X, I have find out the Y, and there I have only taken one component, and if one component I take, the variance is going to be 38%. If I take two things, variance becomes 73%. 73% variance I have covered, and if I take three things, 96% of the variance I have covered, and if I take all four, then the variance becomes 100% variance, because everything I have taken 100% data I have. It is then another example where I have created the data in this way, that instead of 4 I have 5 values: 1, V1, V2, V3, V4, and V5. 5 values. The first value is a number from 1 to n. Okay, number from 1 to n. Second value is a double of the previous number. Second value is just the 2 multiplied by first value, means this 1, 2, 3, 4, 5, 6, then this is going to be 2, 4, 6, 8, 10, like that. So those two things are actually related. And then again the V1 ho gaya, V2, and V3, V4, V5, these things are now random. Okay, I have created the data using command, then all these things are actually now random. All these values are now random, and I again apply the same loop on that. What I get, then if you apply, you see that the first is 75%, second is 93%, third is 99%, and four is 1%, 100%, and fifth is also 100%. You can see that the PCA have actually find out that even if you use 4 component, you would be able to find out 100% of the data. Fifth component is useless. Okay, so you can see this. All this code is available on the slides. You please type and execute and try to see that how you are going to get the same thing. Very interesting application that actually came into the CVPR 1991. Actually, they wanted to do the face recognition. This is called the Eigenfaces, very important seminal paper. Okay. So what they did, they applied a camera and acquired the person's image. Then they apply the sophisticated filtering and the thresholding to find out the where is the person. And they cut the person's face, and the face is stored into the database. Okay, there were 16 peoples from which the images has been captured. 2,500 images has been captured. And then they have developed that if I'm matching this person's image with this person image, so what is the accuracy of the system? It should say no. When I'm matching the same person with the same person, it should say yes. So 96% they were able to achieve the accuracy. It was too high. Okay, how they did it? So for every image they have converted, because image is like this, all the pixels are there now, first pixel, second pixel. So they put first pixel, second pixel, third pixel, this one by one. And when after first line, the second line pixels are there, first second line pixel, then third line pixels are there. By this they have created a vector. And for each of the images they have created the vector, first vector, second vector, third vector. For each of the people they have created this vector. Then they have applied a PCA. After PCA, this data actually changes. As you know, the values actually changes. So if you reconstruct that whatever I have got, what is the image? So this is the image. You can see that this person, this image and this image, this person's image become this. So it's very bad. You cannot understand that what is there. But what happens that into the computers, from the computer's perspective, the features are actually now distinct. Okay, so this database becomes this database, and from when he is going to match this image with the other images, then the accuracy he was able to, the paper was able to achieve was 96%. Very seminal and interesting paper. So that's all for today. That I just suggest you that try to go through this particular paper. Very basic paper it is, and talked in a very simple manner that applying PCA, you got the features that are actually more differentiable as compared to the original features. So that's all for today. Thank you for joining.